Welcome, everyone, and thank you for attending today's presentation on how to achieve safety standard code coverage goals with modern CI-based development workflows. My name is Ricardo Camacho, and I'm the Director of Regulatory Safety and Security Compliance at Parasoft, and it is my pleasure to introduce our esteemed partner for today's webinar, IAR Systems. From IAR, we have Rafael Tobinger, Global Product Marketing Manager, and Philippe Torrezand. He's a field application engineer. Also, we have my colleague Miroslav Zielinski, Director of Product Management at Parasoft. With a sterling reputation in the industry, IR Systems is synonymous with excellence in the realm of embedded systems development. Their cutting-edge tools, including integrated development environments, compilers, and debuggers, are indispensable for engineers building embedded applications. And just like Parasoft, IAR is known for their unwavering commitment to quality, reliability, and innovation. The reason Parasoft and IAR Systems are here together is because organizations seek software testing solutions and toolchains that seamlessly integrate with open source frameworks and that can be automated as part of their CI-based development workflow. You guys are in for a treat. You're going to be seeing a new Parasoft product in action being released this April. And along with IR's toolchain, Parasoft is going to demonstrate how you can remove the challenges of maintaining CI workflows, leverage open source testing frameworks, and address the unique requirements of embedded systems testing for safety and security critical applications. All right, let's take a look at the agenda. First, Mirek will put things in context by touching on compliance, verification requirements, particularly around code coverage and modern development workflows. Mirek will then take us through a demonstration of our new product using IR Systems. We will then pass it over to Philippe, where he will take us through the IR solutions. Then, as part of the summary, I'll also touch on the new product CC++ Test CT, followed by our live Q&A. Before we get started, let's go through some housekeeping. Everybody's microphone has been muted. Also, if you have any questions, please enter them into the questions dialog box. You can do this at any time. Also, this presentation is being recorded and will be made available typically within 8 to 12 hours after the presentation has ended. All right, let's get started. I'm passing it over to you, Mirek.
Thank you, Ricardo. So, before we will see a live demonstration, let's briefly talk about developing safety-critical software. No one doubts that this kind of development is more complicated and time-consuming than ordinary software. Regulated markets have their domain-specific standards. Well-known examples are IEC 61508, ISO 2626262, IEC 62304, and there are several others. These standards require implementing methods, processes, and providing evidence that objectives were achieved. On the surface, it does not look very complicated. Standards include tables with recommended methods and techniques for software development, and teams try to find a way to satisfy relevant requirements. Simply speaking, they look for a way to put a, say, green checkbox next to applicable requirements. Some of the requirements can be satisfied with manual processes involving additional pairs of A's. However, to reduce the cost and improve the efficiency, teams look for tools and automation to help them cope with standards requirements. Static analysis and code coverage tools are good examples of how compliance for some of the requirements can be automated. When applying tools to eliminate manual processes, an important aspect is the tool qualification. For safety-critical development, teams cannot use random tools. They need to use tools that are either pre-certified or can be qualified. Otherwise, putting a green check next to the requirement is not possible. In our session today, we will be focusing on unit testing and code coverage and how to integrate them in the modern embedded development workflows. We will demonstrate IAR's build tools for ARM and Parasoft C++ Test CT working in tandem. We won't be focusing on any specific standard because requirements in the standard around code coverage, unit and integration testing are pretty similar. So when it comes to creating unit test cases, standards recommend various methods to derive test cases. Typically, requirements analysis should be the foundation of the process. New test cases should be based on requirements analysis and they should be linked with requirements. Standards also recommend other methods for deriving test cases like equivalent classes analysis, boundary values analysis, and error guessing. All these methods are geared towards assuring the completeness of testing. And documenting the completeness of testing is a very important aspect of the process. It's typically achieved with two types of reports. Requirements traceability report, which demonstrate testing result in the context of requirements. These reports help identify unimplemented or untested requirements, and code coverage reports, which demonstrate completeness of testing at the code level. Code coverage reports help identify code sections that were not exercised during testing process. For the code coverage, several metrics are mentioned in the standards. There are some differences in the requirements between the norms, but in general, without going too deep into details, statement and decision coverage metrics are typically required for the lower safety integrity levels. These metrics are relatively easy to understand, and achieving 100% coverage is typically not too time consuming. But for the most stringent systems, standards require the application of MCDC coverage. Achieving MCDC coverage goals can be daunting. We need to demonstrate that each condition in a decision independently affects the decision outcome. This can take some time, especially if we work on testing and coverage long after the code is created. Achieving MCDC coverage goals requires good understanding of the code logic and preferably the code's requirements, but even then assuring completeness adds a significant time to the testing process. In a few minutes in our demo, we'll present how build and test tools facilitate this process in modern development workflows. Workflows that are nowadays typically based on the popular CI platforms such as GitHub, GitLab, or Jenkins, and are driven by Git branching and merging actions. In these workflows, ease of automation for tools is absolutely critical. It helps teams to stay effective with growing requirements for compliance with safety, security, and quality standards. And ease of automation for tools is enabled by light command line interfaces, no IDE dependencies, support for Docker containers, Kubernetes, and Linux ecosystem. Teams understand now that standards compliance is not something that can be added to the product later in the process. It must be an inherent part of the development workflows from the beginning. Otherwise, the cost exponentially grows. So, from our observations, we see now that testing against standards requirements, be it MISRA coding guidelines or unit testing with code coverage, is tightly integrated with the automated pull request quality gates. Prototyping and fast development with relaxed compliance requirements is typically done in the dedicated branches, but only compliant code can pass through pull request quality gate and be merged with the master branch. These orthodox rules help avoid, say, compliance debt accumulation and eliminate unnecessary risk and stress before audits. Now, We also see that teams try to avoid vendor lock for compliance assets that are expensive to create, such as unit tests. This is why open source testing frameworks like Google Test, CPP Test, or Boost Test are so popular. So to conclude this part, when looking for build and test tools for safety critical software development, teams prefer solutions that are pre-certified and supported with the qualification kits. Teams also prefer tools that are easy to automate at scale, which means light and simple command line interfaces. Tools that are tightly integrated with IDEs and graphical interfaces are not a good fit for the CI workflows. Another important aspect is the ease of containerization. Containers bring numerous benefits, particularly for highly automated setups, reducing maintenance cost. And finally, as we briefly discussed on the previous slide, for the test tools, teams now prefer solutions that can integrate with the open source testing frameworks, augmenting them with additional features required for standards compliance. And now, on to the demonstration. In our demo, we'll go through the following sequence. We'll start working on a new code in a feature branch. The code will be developed and tested locally at developer's desktop, including code coverage metrics. Then the pull request will be created. The integration will be rejected in the first attempt due to insufficient code coverage. We'll improve testing, and after applying fixes, code will be successfully integrated. For the integrated code, another pipeline will be executed, and the complete quality and compliance results will be collected in the reporting and analytics dashboard. So, let's see it in practice. Our demo project is hosted in GitHub. Here we have a local clone of the repository. Our development team uses a modern CI-based development workflow. All pull requests go through automated quality gates that include unit testing and code coverage. Our development toolchain is fully containerized and includes IIR and Parasoft tools. The same container image is used for the local development and for the CI pipelines. Project build is configured with CMake, with Parasoft and IIR's tools integrated into it. Now, let's assume that for our project we need ISO 26262 ASIL-D compliance. So we need to demonstrate completeness of requirements testing and document 100% of statement, decision and MCDC coverage. For testing at the unit level, our team selected CPP Test, a popular open source testing framework. Our project so far was developed with limited attention to compliance. But now, for the new code, we have a goal to start tracing our unit testing to requirements and monitoring code coverage. So let's say that our task is to implement getAverage function, make sure it's tested and complies with requirements. We do have a set of low-level requirements for this function. As a developer, I've analyzed the specification and implemented the first version of getAverage function. I've also added the first couple of unit test cases. You can see them here. Please note that test case names have requirements IDs added as suffixes. That's one of the available ways for correlating tests to requirements. It establishes the test to requirement link and enables generating requirements traceability report. Now, I'm interested in whether my new code works, all tests pass, and if I have sufficient code coverage for my newly implemented code. Let me build the project, run new tests, and generate code coverage reports. The great value of IIR toolchain is that it comes with a simulator and a convenient command line interface to use it. This enables fully automated workflows that include testing. Later in the cycle, once the hardware is ready, we can use the same easy-to-automate interface to execute tests on the target. As you can see, the code was built and tests were executed. And now Parasoft C++ Test CT generates code coverage reports. Alright, it seems all our tests passed and we have coverage reports generated. We see a brief summary of the coverage results in the build console. We also have report files generated in the .coverage folder. Our demo setup includes text and HTML reports. But for me, as a developer, the most convenient way to analyze the results is with decorations in the VS Code editor. So let me use Parasoft VS Code extension to load coverage results. Let's start with something simple with line coverage. The brief analysis shows that our testing is incomplete. We still do not have 100% line coverage. We are missing a test case which examines the function with null pointer as a buffer. Let me quickly add this test and make sure it's correlated with a requirement. And execute my test again. We expect coverage for the getAverage function to increase. And indeed, it seems we now have 100% line code coverage. We are now ready to push the new code to the repository and create a pull request. My pull request triggered the automated pipeline. The pipeline goes through several stages, including code coverage quality gates. Let's take a look at our pipeline definition file while it executes. Here the Parasoft C++ Test CT is integrated with the CMake build. No other special actions are required for the integration. Our default target includes building CPP test unit tests. Here we execute binaries using IIR's simulator. And here we invoke reporting targets added by C++ Test CT CMake extension. Once the code coverage report is generated, it's published to the GitHub pages so the team can easily access it. Below are code coverage quality gates for line and MCDC coverage metrics. Our current requirements for the quality gates are 100% statement and 90% MCDC code coverage for the new code. Let's go back to our pull request and see the pipeline's results. It seems we have a problem with MCDC coverage. Our line coverage quality gate passed, but the MCDC quality gate has failed. We simply did not achieve expected 90% of MCDC coverage for the new code. To understand the gaps, we can review the HTML report published on GitHub pages. Or what may be more convenient for developers, we can view results using the VS Code extension. C++ Test CT VS Code extension integrates with GitHub and automatically downloads the most recent results for the working branch. It simplifies coverage feedback analysis and reduces the cost of compliance processes. When my pipeline fails, I need 10 seconds to get results in my VS Code and analyze gaps in the most convenient way. So let's see pipeline's MCDC results for our new code. We have 3 decisions in the function. For 2 of them, we have achieved 100% MCDC code coverage. However, we still don't have the complete MCDC coverage for the second decision, where we test control values of the indexes. Let's take a closer look. C++ Test CT provides extended MCDC coverage reporting that helps understand coverage gaps. In our situation, we have 4 conditions in the decision. The first 3 conditions are already covered according to MCDC coverage requirements. However, we still don't have the coverage for the last condition. Parasoft toolchain provides a great value here. Extended MCDC reporting provides hints that help understand the coverage gap. Here we have a list of test vectors that were executed. It includes information about the values that conditions were evaluated to and the outcome of the entire decision. This table helps in understanding which test vectors cover specific conditions. Below, we have the information about missing test vectors. A great value is that the tool computes the minimal set of test vectors required for the complete coverage, helping developers to be more productive. In our case, we need a test vector to evaluate the last condition as true, while all other conditions are evaluated as false. Let's add this test case. In general, depending on the situation, different actions may be required to eliminate the coverage gaps, including changes in the implementation, modification of requirements, and the addition of missing test cases. In our case, the code was correctly implemented following requirements, but the developer forgot to add a test case for a specific scenario. The problem was detected thanks to C++ Test CT-based quality gate. Let's make sure our new test case is correlated with appropriate requirement. Now we are ready to push the code again. This operation triggered a pipeline for our pull request. Let's give it a minute to finish. Alright, it seems our coverage quality gates passed, and we are ready now to merge the code into the master. For the master branch, we have a dedicated pipeline verifying integrated code. This pipeline executes extensive set of tests and monitors the code coverage for entire project. Our merge operation triggered this pipeline. The results of this pipeline represent the current status of our stable branch. Our pipeline sent these results to Parasoft DTP, the reporting platform. Parasoft DTP aggregates inputs from different types of testing and presents results in graphs, trends, and compliance reports. With these widgets, I can monitor my progress in various compliance aspects, including the progress with the code coverage. I can also check the progress with requirements implementation and testing. With this widget, I get information about the number of requirements already covered with test cases and those that are not and require attention. The dashboard information allows me to react if my progress with compliance goals, including code coverage, is too slow. This kind of insight is essential for any persona involved in safety, security, or quality process management. And this is the end of our demonstration. Let's recap. In our demo, we presented a CI-based workflow with GitHub where IAR and Parasoft toolchains were used to satisfy unit testing, code coverage, and requirements traceability reporting objectives stemming from the safety standard. We have gone through the following sequence. Developers started working on the new code in the feature branch. Here, Parasoft's and IAR's toolchains were used on the developer's desktop. Then the pull request was created, where toolchains were used in the build and test pipeline. code was rejected and developer downloaded pipeline results to the local IDE for remediation. After applying fixes, adding new test cases, code was successfully merged. For merged code in the master branch, another pipeline was executed. The master pipeline results were sent to Parasoft DTP for trends and compliance status analysis. During our demonstration, we used a containerized development toolchain, including Parasoft's and IAR's tools. This containerized toolchain was used by developers on their desktops and for continuous integration pipelines. To help you understand more about our toolchain, I will now pass it over to Felipe. Felipe will share information about the benefits of using IAR's tools. Felipe, the stage is yours.
Thank you, Mirek. I would like to start with this slide showing a table with the current IR solutions that we have for ARM, starting with the IR build tools for ARM on the first column. This product was designed especially for the continuous integration, where you can build, analyze, and run non-interactive tests for your application, mostly on the server side in a headless mode operation. It requires a network type license, and it's a cross-platform product, meaning that you can install it on Windows or Linux. The next product is the traditional IR embedded workbench for ARM, where you have mostly the same feature set, plus the embedded workbench IDE, where you can actually develop your applications and perform interactive debugging in a graphical user interface way. And then on the last two columns, those products have their own particular functional safety edition. So you have functional safety edition for the IR build tools, as well as the functional safety edition for the IR embedded workbench. The difference for those special editions is that all the compiler, assembler, linker, everything that you can use to build your application is pre-certified for you, which means that you can simply start using that for functional safety encumbered designs, as well as we recently introduced as well the IR CStat. It's the static analysis tool add-on that's optional, and it's also pre-certified for functional safety as well on both flavors, on both the IR embedded workbench and the IR build tools. So here's an outline of what the functional safety edition of the IR compiler contains. You get basically the simplified validation process because the toolchain is already pre-certified for you. You just start using it. It comes with a TÜV SÜD safety certificate, the safety report, and also a guide of hints, tips, and advice for you engaging into safety critical designs, the IR safety guide. It's included with the product. It's a PDF that you can read, and it will give you several advice for you to move faster with your certification process. Important to mention here as well that functional safety users get long-term support, which means that you have a special support agreement, revalidated service packs that you can install on top of existing installation, because sometimes we might come with some service packs that we release after the initial release are revalidated and recertificated, so you can safely install on top of that. Important to mention that the Functional Safety Editions doesn't provide the newest features as in the regular versions. They are feature frozen. It's only for eventual fixes that might be found after the initial release. And here is an outline of what kind of standards that the compiler is pre-certified for, ranging from industrial up to household appliances, depending on the target architecture that you use. It might cover up to 10 different standards, which means that in this case, ARM and RISC-V targets has the most covered among the all supported standards. Here you can have an outline of the IR build tools for ARM version 9.50. Those, as I mentioned before, are designed for continuous integration, headless operation, which means that you get the command line tools and they are cross-platform, meaning that you can have the installer for Linux that runs on Ubuntu or Red Hat, or else on Windows. Those are very easily deployable on the typical CI/CD environments such as GitHub, GitLab, Jenkins, and others. On the latest version, we introduced the cSpyBet, which is our proprietary debugger that gives you the capability of running non-interactive tests onto your code, and it's very useful for automated tests. On the right-hand side of the slide, you will see IR Build, which is a utility to build projects created with the embedded workbench, as well as cSpyBet, just as an example. This slide gives you an outline of how we see the DevOps workflow for embedded software when you're using IR. So you start with the embedded workbench, do your code debug and commit cycle, and every time you push code to a continuous integration orchestrator such as GitHub, it will trigger a workflow that's defined by you, which will run several build, test, analysis, and quality gates as you see fit for your purpose. And for every job, you will probably run it into a self-hosted runner. A self-hosted runner runs on your network, private network, where you will have an IR license server serving multiple licenses for each one of those runners with the IR build tools installed on that. And with cSpyBet on the latest version, you can also use the iJet. It's the IR debugging probe to run automated tests directly on hardware as well. So why do we recommend Linux for CI? Just because it's faster. You get your projects built in the half of the time and your code analyzed in 1/4 of the time. So for serving a whole team of developers, this is the recommended option. This is an outline of the different IR debug probes available. On the left you see the iJet, which is your everyday probe, and on the right you see the iJet trace, which is a superset with ETM memory capabilities for deep trace and code coverage purposes. So you can use both with both products, as well as with the IR embedded workbench for RISC-V. So those two probes can be used with both ARM, all the ARM cores that are supported in your products, as well as for the RISC-V cores. I would also like to mention that we recently released a couple of Visual Studio Code extensions from which you can build your embedded workbench projects, run cstat for static analysis, and you can switch back and forth very quickly among them if you want to change a project option. Another extension is the IRC-SPY debug. The IRC-SPY debugger will be able to debug an executable that you built from embedded workbench project or even a CMake project, for example. And then it will use behind the scenes the native IRC-SPY debugger, which comes with a built-in simulator, multi-core debugging capabilities, and supports all the devices that you have available and supported on the embedded workbench, as well as RTOS thread awareness. So if you're interested to know more about CI with IR, you can go and visit our GitHub page at github.com/irsystems. Here's an outline of our most popular repositories with examples and tutorials that are available on GitHub. And now I will give the word back to Ricardo. Thank you.